You're watching a Channel 98 NBISD TV production.
From the basement of New Braunfels Independent School District Central Offices, I'm Kevin Corpy, and this is That Geometry Show. Now, today's show, we're going to be looking at three-dimensional objects again, but we got something very interesting planned. We're going to be doing a lot of different things with them. We're going to be designing sheds, we're going to be wrapping presents and cutting up boxes and peeling labels off canned goods and measuring them. Sounds like a typical Friday night for me. But we're going to do it on today's show. I'm going to share it with you. So grab those worksheets off the website, grab a sharp, pointy pencil, number 2, of course, and let's get going. Okay, lesson 23, a goodie. This is going to go along with your geometry textbook 11.2, nets and surface area. Okay, when we're discussing three-dimensional solids, it is natural to talk about certain quantities. In this case, we're going to be talking about that solid's surface area, which is basically the sum of all the areas of the outer surfaces, or from last time we called them faces. Now, when would this come up? Well, perhaps you're painting the exterior of your house, or my house, if you'd like to do that. Or you're wrapping a giant gift for someone, maybe for me. The amount of material that you're using, whether it's paint or paper, depends on the surface area of that solid object. Okay? Now, the area of a surface, we haven't talked about that, so we're going to kind of talk about that first and put them together on a three-dimensional object. But the area of a surface or a polygon is nothing more than the measure of how much space that polygon takes up in the Euclidean plane, on a two-dimensional plane. It's measured in square units, like your house. Your house has a certain square footage. That's the amount of living space on the floor that you have. Think of the area as the number of squares that it's going to take to cover a region completely. Like if you have any tile in your house, maybe in the entryway or in the kitchen, those tiles are probably 12 by 12, 1 foot square. If you think about trying to tile an area, the number of tiles that you use would be the square footage. Okay? Now, many common shapes in geometry actually have formulas that we can use for finding the quantity of the area. And here's some real common area formulas that you're going to be responsible for using, if not memorizing. Okay, there's lots of them on here. The first one is our square. And I'll zoom in here so that you can kind of see more specifically each of these. We have a square. And a square, remember, is composed of two congruent sides. So the area A is nothing more than S times S, or S squared. We have a circle, which is pretty common. The area of a circle is pi. Pi is just an irrational number, 3.14159 ... times the radius squared. So pi r squared. Then we have a rectangle. A rectangle's area is A times B. It's like a square, except A and B are not the same. So it's just the product of the two side lengths. Then we have a triangle. A triangle's area is 1/2 the length of the base, which is this one here, times the height, which we called an altitude on a previous lesson. We also have a parallelogram, similar to a rectangle. It's the base, which is one of the side lengths, times this altitude, which we're calling h, and this is an exterior altitude. An equilateral triangle you can think of as being carved out of a square. It's a fraction of a square. It's the square root of 3 divided by 4, or the square root of 3/4 of a squared, where a is one of the congruent side lengths of the equilateral triangle. We have a trapezoid. We've talked about that on a previous show. The trapezoid is 1/2 the sum of the two parallel bases, base 1 and base 2, or their average length, and we multiply that by the height, which is the altitude. Then we have the rhombus. The rhombus's area is 1/2 the product of the two diagonals, d sub 1 and d sub 2. And finally, we talked about this last time, the area of a regular polygon, any polygon with n sides, where all the sides are congruent, is 1/2 p, the perimeter, times a, which was the apothem, remember. Okay? So those are some of the area formulas. Your teacher might give them to you on a test. Make sure you ask which ones you're responsible for memorizing, because some of these you probably do have to memorize. Okay, so how do we find surface area? Ooh, zoom right back out. There we go. So finding surface area really just involves these 3 easy steps. Number 1, we want to determine which shapes make up the sides of our three-dimensional solid. Then we want to apply the correct formula, either from our head or from the sheet, to the respective side to find its area. And number 3, the funnest part of all, we just add up all the areas of the faces and we'll have the surface area. Now here's an important note. Since area does involve side lengths, there will be units. Okay? Problems that have units, the units need to be there in the end in your final answer. Also, be sure that the same units are there for all your measurements. For instance, you cannot multiply feet times inches. It doesn't make a square measurement. So talking about that floor tile from earlier, if we look at it like this, if I have 1 foot and 12 inches right here, let's call that a square because 12 feet and 1 inches are the same. We would not say that the area is 12 times 1 or 12, because if you look at the units, it's inches times feet. That's not a square unit. What we need to do is call them both 1 foot or both 12 inches. So what we can say, though, is that 1 foot times 1 foot is 1 foot squared, or 1 square foot. Or if we use the inches, we could say that's equivalent to 12 times 12, which is 144 inches squared, or square inches. Okay, so the units have to be the same. And when I do the calculations on today's examples, I will be including units in my calculations because it's another nice way at the end to make sure that we've got the right answer. All right, so let's wrap some gifts. Here's the scenario. My wife just celebrated her birthday last week, and so I kind of pulled this example right out of my own life. I was wrapping a box for my wife. She really loves boxes, and she's really excited when I get her boxes. Well, here's a box that's 4 centimeters long, 5 centimeters wide, and 10 centimeters high. Now, it's not important that we're calling one width, one height, one length. What is important, though, is the fact that we have the 3 sides labeled. There's just 3 dimensions. We want to find the surface area of the box. Well, this box has 6 faces, and they come in 3 pairs of congruent faces, so that this shaded side here is congruent to this side here. The front of the box, the rectangle we're staring at here, has a partner in the back that's congruent. And then we have the top and the bottom, and those are both congruent shapes. So to find the surface area, I can just find the area of each of the 3 unique sides, double them because there's 2 of them, and add them all together. So let's see if we can do that. So the surface area, and I like to put SA, because it's surface area, not just area of one of the faces, is equal to 2, that's going to stand for my 2 sides, and it doesn't matter which one I choose first. Let's stare at this box head on. I've got 5 times 10. Okay, this is 10 if you need to label it. So this is a rectangle. This is 1 dimension. This is the other dimension. So 2 times 5 centimeters times 10 centimeters. Again, including the units is a nice check. Plus, well, now I need to go to another side. Plus 2, I'm going to switch colors here. I've already done the front, 5 times 10. Let's do the shaded side here. It is 4 centimeters times the height of 10 centimeters. And then I'm running out of room, so I'll wrap down here. Plus the other side, let's do the top and the bottom. The top and the bottom are congruent, so I have 2 of them. And I need to carefully look on the diagram. This is one of the dimensions, and it is 5 centimeters. And then the other dimension is this, which is 4 centimeters. Okay, so now all I got to do is do the math. The different colors show the different sides. There's 3 unique sides with a congruent partner. So notice what happens here. If I multiply 5 times 10, I do get 50, but I get centimeters times centimeters, which is square centimeters, and that's good, or centimeters squared. Plus 2 times 4 times 10 is 40 centimeters squared. Plus, I'm going to squeeze it in here, 2 times 5 times 4 is 20 centimeters squared. Okay, now they're all centimeters squared, so they're all like terms, which is really important because we can add like terms. But before I do that, I'm going to go ahead and multiply each of them by 2. So I have 100 square centimeters plus 80 square centimeters plus 40 square centimeters. And that grand total comes out to 120 plus 100 is going to be 220 centimeters squared, or square centimeters, however you want to say it. So that's a reasonable unit for area. And that's basically the amount of material at the very minimum that I'm going to need. So if I was to wrap that box, I would need at least 220 square centimeters of paper to be able to get it in there. Okay? Now this example was pretty easy. This perspective drawing is a 2-dimensional representation of a 3-dimensional object, and it was pretty easy to get the depth and get the 3D effect out of it. But there's 2 other ways that we can do that. One of the other ways to help visualize three-dimensional objects in 2D space is by looking at what's called a plan and its respective elevations. So a plan and the elevations. Now, we looked at these actually last time. It's the two-dimensional representations that we looked at: the front, the side, the left and the right views. Well, the plan is essentially the view from above, and the elevations are the side views. And if you've ever seen an architectural drawing or a blueprint, you're already familiar with this. The blueprint is basically the floor plan of the house. It's remove the roof, and you're looking down inside so you can see where the interior walls are and all the fixtures and everything. What we're going to look at is from above, but we're going to keep the roof in place. So we're going to be looking at essentially a roof plan, and the elevations on the architectural plan are going to be the side views, what the house looks like from the outside. It's the same thing with any three-dimensional object. Now, here's an example that should shed some light on what I'm talking about. And speaking of sheds, we're going to design and build a shed here. Okay? So let's go ahead and draw the plan and the elevations for this following shed that we want to build, and then we'll determine the amount of exterior sheathing that we need. Now, sheathing is a good word. It just means the amount of material that we're going to need to cover the exterior of this shed. We're not going to cover the floor. We're going to assume we're building it on an existing foundation. So the sheathing might be the plywood to wrap around the sides, and maybe the roofing or the decking material for the roof. So it's basically finding the surface area. It's just a fancy name. Okay, notice the dimensions here. We've got 3 meters high, which is approximately 10 feet. We got 6 meters wide, which is about 20 feet. We have 6 meters deep, again, which is about 20 feet. And then we have these little roof pitches. This is called the gable portion of the roof, the part that's a triangle. And it's on a slant 4 meters, which is about 13 feet by 13 feet. Okay? We also want to notice that this front view here is a rectangle situated underneath a triangle. Okay? So let's go ahead and draw the plan. That's from above, and the elevations. All right, well, I took the liberty of actually having them drawn for us so I can just demonstrate and point to it. Now, imagine you're up on top of the roof, maybe in a tree, looking down over it, or in a helicopter. That's cool. You're looking straight down, and what do you see? You see this right here. This right here is actually the ridge of the structure. Whoops, there you go. This is the ridge of the structure. So we're looking at shingles right here. These would be the shingles that we're staring at, assuming we did use shingles. And this line right here is the ridge. But notice from above, we've got a rectangle here and a rectangle here. That's the plan. It's the roof plan. We're looking down from above. The front elevation, again, we're staring at it head on, and this is equivalent to the rear elevation as well. We've got a triangle on top of a rectangle. And the side elevation, now when we're looking from the side, this right here is the roof line. And so we're actually staring at some of the shingles, which remember are going to be right here. And so we want to make sure that we don't want to count those twice, and I'll show you what I mean. Let's go ahead and find the surface areas based on these different drawings. Okay? Let's go ahead and start with the roof right here. It's 2 different rectangles. The surface area of the roof, if we remember the dimensions from the other side, this was 4 meters on the slant, and so was this. This was 4 meters on the slant. And it was 6 meters long. So what I can do, I can think of it as one big rectangle, but I'm going to think of it as one rectangle here, and I'm going to double it. So this 2 is for the 2 different panels, and I've got basically a rectangle, so 4 times 6. 4 meters times 6 meters. Well, that's 2 times 6 times 4 is 24. And again, notice meters times meters is meters squared. That's square units. That's good. Now 2 times 24 is 48. So I know that the roof itself is going to require 48 square meters, which is approximately, if you're interested, about 517 square feet of material. Which means if we go to the store and we're looking for shingles, we're going to need to get enough to cover about 517 square feet of region, of area. All right, now the area of the front and back are the same, so we can double the calculation of 1. Now we can find the area of the lower rectangle, this one here, and we can just add it to the area of the triangle. So triangle's area plus rectangle's area. Well, the triangle, remember, the formula was 1/2 the base times the height. Well, the base is up here, and we remember that all the way across was 6. I'm going to need the height, so I have to drop that altitude down, and I'm going to call that h. Well, because this is 4 and this is 4, this is an isosceles triangle, so we're using stuff from other shows. So this altitude is also the perpendicular bisector. So if it was 6 all the way across, that means that this is 3. And now in a right triangle, if I'm trying to find one of the side lengths, I can use the handy-dandy Pythagorean theorem. So down here, I'm going to call it the P theorem. I know my two shorter legs, 3 and h, so I have 3 squared plus h squared equals the hypotenuse, which is the pitch or the slanted roof portion, 4 squared. And I'll solve, and I get h squared equals 16 minus 9, taking the square root of both sides. We get h is the square root of 7 meters, which is approximately 2.646 meters. But I'm going to use the square root of 7 on my interior calculations because it's an irrational number, and I don't want to get rounding error. Okay, so now that I know that, I can find the surface area of the front and rear elevations. So here we go. Surface area is 2, that's for the front and the back. The base rectangle is going to be 3 tall. Remember, this was 3 by 6. So 3 times 6 is right here, 3 times 6, plus the area of the triangle, 1/2 the base. Well, the base is the triangle all the way across. It is 6 all the way across. So that's this, times the height or the altitude. We just found that square root of 7. All right, so now all I have to do is do the math. I've got it all set up. The hard work's done. Meters times meter is square meters, so 3 times 6 is 18, plus half of 6 is 3, square root of 7. And there's doubled. So now what I'll do is I will distribute the 2 all the way through, and I get 36 plus 6 square root of 7. Now, this is the exact answer. Okay, it has no rounding error, but it's kind of hard to get a feel for exactly what that is. So if we round, we'll go ahead and round to 3 decimals, or I will in this case, and I get about 51.874 square meters. All right, well, that's just the front elevation. Now we got to do the sides. The side elevations, remember, we're staring right here at the shingles, and we've already counted the shingles, so we really don't need to count those again. We just want this lower portion. Okay, so let's go ahead and do that. There is 2 of them, 1 on each side, so the surface area is 2. It's just a rectangle, so it's 3. That was this height right here, 3 meters by 6, the other dimension. It was 6 meters deep, and I get 18 meters times meters is meters squared, double to get 36. So now I've basically found the area of all the components. So the total exterior surface area is nothing more than the sum of all our quantities that we found. So here we go. The grand total. The surface area of our shed is 48 meters squared, the roof, plus 51.874 meters squared, which is the front and rear. And I use the square root of 7 when I punch that in. And plus 36, the sides, gives us 135.875, rounded to 3 decimals, square meters. Okay, now that's going to be about 1,462.541 square feet, and that's going to be basically the total coverage of our shed. All right, take a quick break while I hammer out the details from the shed, and we'll be right back. Ow, my thumb!
When you give up the ability to decide for yourself, you give up what makes you, you.
This is a wonderful resource for the district, for the students to come to and the parents to come to, because I can answer those questions on where to start and you know, what's the first step you need to take in order to make college a reality. There's a lot of resources in here. There's a lot of printed material, and of course we have 16 computers, and I recommend don't ever pay anybody to pay for a scholarship search, because those are things that we can do for free, and I can show you how. I had a senior who was not sure that she was ever going to make it to college, and she got into UTSA. I'm so proud of her. She's very successful. I just heard from her recently. She got a very large chunk of financial aid through her research efforts. Come visit us. We're here. We want the word to get out to the community that this is a resource that NBISD provides for our students, and take advantage of it. It's free.
right, let's get away from construction for a while and get to something that has something that's more in common with catching butterflies. You curious? Yeah, let's go take a look. The second way to represent a three-dimensional object surface area in a two-dimensional plane is by something called a net, which incidentally, by the way, if you're wondering, is something you can use to catch butterflies. So that completes the bad joke. All right, imagine you can cut a cardboard box along any of its lines and you can lay it out flat. It might look something like this, okay? Cut the edges, lay it down flat. Once it's flat, you obtain what's called the two-dimensional net. Now, depending on how you cut the box, you can obtain a different, it'll look different, but it'll still be the same box originally. It'll be equivalent, and we say it's an equivalent net. Now, this is a little more useful than the multiple drawings because it is only one representation, and we are staring at it flat down on the paper. So if we can find the area of the flat object, we don't have to worry like we did in the shed example about counting the roof twice. We just find the area of what we see laid out flat. Okay? So let's look at this example. Which of these following down here are going to be nets for this cube above? Interesting. This takes a little bit of practice. A cube has 6 sides. So if I cut this out and laid it flat, which of these, if any, would work? Well, we know it has to have 6 sides, so I have to have at least 6 squares. Notice B, 1, 2, 3, 4, 5, has only 5 tiles. So it cannot work. One of the easiest ways to get used to these originally, or initially, is to actually cut these out and try to fold them up. And I've done that here for you, okay? So let's look at this first one here. It's 6 squares all in a row. And so I have 1, 2, 3, 4, 5, 6. If I try to fold this back up, will I make this the cube? Well, I've made the square, but see this extra flap? It's in the wrong place. I need 2 more squares, but I need one top and bottom, and all I'm doing is I'm wrapping it around. It makes a pretty tight little box, okay? Maybe you can put a votive candle in there and it'll look cool, but the top's not there. So that one will not work. Let's get rid of that. Okay. Let's look at the next one here. Well, we know it doesn't work because it doesn't have enough, but there's a nice depiction of it. If you fold it up, will it make the cube? Well, let's see. Ooh, it looks like a cube, right? But like any good magician, there's the secret, and that is the bottom. There's nothing in here. That's where that 6th one came from. So see you later. Gone. All right, let's look at part C. Looks like a cross there. That's this right here. If I fold that one up very carefully, the purple fold, I fold this up here, and I fold it, and I turn it over. Will I get a cube? Well, I have all 6 sides. And it appears, if I rotate, that I do. So yes, this one actually appears to be the cube. So we have a winner. Now, are we done? No. Careful reading. Which of the following are nets? That's plural. That means there might be more than one. So let's proceed to the last one. It looks different, but is it equivalent? Well, it looks something like this one here. Okay? If I fold this guy up, there's the side, there's another side, doing good. Fold him up, got the other side, fold it over, I have the top, and put all the toys in the toy box, close the lid, and it looks like, yes, in fact, we do have another equivalent net for the exact same cube. So we have 2 answers. That's a net, okay? Cut up a 3-dimensional object, lay it down flat. Now this net is useful for determining surface area because we've reduced the problem to finding the area of the 2-dimensional solid. We don't have to worry about double counting anything again like in the roof example. Now sometimes drawing these nets on what's called isometric dot paper is a very useful way to depict them because isometric, remember, means rigid transformation, and so the dots are basically rigid points that help us to count the spacings here. So to the nearest whole number, find the surface area of this square pyramid using the net. Well, square pyramid, remember, has a square base. All the sides are equal. This is the net of it, okay? If you imagine cutting this pyramid along its spines right here, which looks something like this, and you cut it and you lay it down flat, what does it look like? I want my mummy. Bad joke. Okay. How do we know that this is 3 and 4? This is the same depiction that I have right here, but the isometric dot paper allows us to count. So we count the number of dots. 1, 2, 3, 4. So this is 4, and the altitude is 1, 2, 3. So the triangle is 3. And so that's how I came up with these dimensions here. So notice I can now find the area of this triangle, this triangle, this triangle, and this triangle, and they're all congruent. So I can find it once and multiply it by 4 and add it to the square base. Well, let's see if we can do that. So the surface area is going to be, let's get the square base out of the way. It's 4 by 4. So it's 4 units squared times 4 units squared, or 4 squared, plus, now we're going to have 1, 2, 3, 4 of the triangle. So the formula for the triangle is 1/2 the base. Well, the base is 4 times the height, we counted from the paper, is 3. And again, we've set up our problem, so now we have to do is complete it. 16 plus 24 gives us 40. Now, these are square units. I know we weren't given anything specific like centimeters, but it's a good habit to get into if you're not given any, just to put units squared. All right, it's time for the say what? Yep, already that time. My favorite part of the show. Sometimes we are only interested in a portion of the surface area of a figure. For instance, in a right circular cylinder, like a can of food, we might want to know what the surface area of the label only is. This is called the lateral surface area. And remember, lateral means side. So imagine we start with this. This is a cylinder. If I cut right down the side here, peeled the label, and start peeling it off, we'll do this in reverse. Let's say this is number 1. I start peeling off the label. Number 3, here's the label unfolded. It looks like a rectangle. Wow, okay. So this would be the lateral surface area of the cylinder. It's really just the area of a rectangle. All right. Well, what is going to end up being the height of my rectangle? It's the same thing as the height of my cylinder. I'll call it h. All right. But notice that the length here is going to end up being this distance all the way around the can. And that's all the way around the circle, and we called that the circumference. The circumference, one word, I couldn't fit it in there. Okay, now the circumference also has a formula. It's 2 times pi, which is 3.14, times the radius. So if I substitute that back into my rectangle area formula, the area of a rectangle is going to be the height times the length. But I know that the length is really 2 times pi times r. I can substitute that for L, and I get h. And that's going to be the lateral surface area of the cylinder. So I got a real juicy example here to help demonstrate it. All right. Find the lateral surface area of this can. Okay. It's pineapple juice. Yum, yum. I like to drink it after a good math problem. Really revitalizes me. Okay. Not really. Notice in this diagram we have some dimensions labeled. We got 5.5 inches, and that is the distance all the way across. That is the diameter. Okay, we don't want to be fooled. That's the diameter. And we have the height of the can is 7.75 inches. So we want to figure out what the lateral surface area is. So let's pull out the equation. It's going to be 2 pi r, which again is the circumference all the way around here of the top of the can, which forms the length of the rectangle, times the height, h. Well, I need the radius and I have the diameter. So if the diameter is 5.5 inches, the radius is just half of that. So the radius is 2.75, half the diameter. Okay? And the most common mistake is just to take the number 5.5 and jump right to the equation and plug it in. So read carefully, make sure that you have the correct information. Now I can plug in. So the area, or the lateral surface area of the label is going to be 2, that's the number 2. Pi, I can use 3.14 approximately, times the radius is 2.75 inches, times the height, and I'm running out of room, so the height is I'm looking at the wrong place. It's 7.75 inches. So I have inches times inches, which is going to give me inches squared. And if I punch all that in on the calculator, you actually have a pi button on your calculator, you get 133.910 square inches, or inches squared. Isn't that amazing? So you see, math is all around us. It's in our backyard in the shed. It's under the Christmas tree in our gifts. It's in our pantry on our canned goods, and it's definitely right now on your TV screen. So thank you for letting me take up the surface area of your television screen today, and I hope you let me do it again real soon. Until next time, I'm Kevin Corpy, and I'll catch you on the flip side.